Okay. All right, so welcome back to another exciting session of CE 374 Urban Stormwater. I got a couple of quick announcements for you before we get started. First, I've extended the deadline of homework 1 until Tuesday because I haven't covered all the material needed for that homework. I will be covering the remainder of the material needed for homework 1 today. And it will be due on Tuesday. Please come see me at office hours today at 5:30 if you have any questions. I will be there from 5:30 to 6:30 today. Okay, and Becky has office hours on Monday from 2 to 3 as well if you need last minute office hours. Okay. Homework 2 will be assigned soon, and that will be on our next subject in the class, which is hydrology for stormwater design. A quick comment before I move on. If you're going to be late to class, if you know you're running late and you want to let us know to excuse the lateness, just email Becky about that or message Becky about that so that she knows when she's taking attendance, okay? Great. Are there any questions before I move on? Yes. Sorry? So if you sit in your assigned seats, Becky will just take attendance based on who is sitting in their assigned seats. So just make sure you're sitting in your correct seat and you will be counted present. Okay. Okay. Any other questions before I move on? No? Okay, great. Well, let's get started. Last time we finished up our conversation on channel transition problems. So this is the mystery problem where we had flow in an open channel encountering a transition in the bottom elevation of the channel. And we saw that that transition in the bottom elevation of the channel changed the flow over the surface of the transition, which could potentially lower the surface of the water. If the approaching flow is subcritical, it could raise the surface of the water if the approaching flow is supercritical, and it can even possibly cause the flow to go through the critical depth, which will change the flow regime, possibly on the other side of the transition. We also discussed kind of the intuition behind what critical flow is. So you've seen critical flow in hydraulics, you know the equations that describe critical flow. In last class's session, we discussed what critical flow kind of means intuitively and physically. And we discussed how critical flow occurs when the velocity of the water itself is the same speed as the speed of a wave traveling through that water. And this has implications for whether disturbances from downstream can propagate upstream. So this has important implications for design, which we're going to see later on when we encounter culverts in particular. Okay, are there any questions on the material we covered in the last class? I will be revisiting something from the last class because there were a couple questions on it. Are there any other questions on material from last class before I move on? Okay. Today, we are going to be finishing up our discussion on open channel flow. We're going to be discussing discharge control structures, which you will need for homework 1. This is for the last couple of problems. And we'll also begin our module on hydrology for stormwater designs. This is going to encompass the next 4 or so classes, and we're going to discuss kind of the basic hydrology that you need to know in order to do stormwater design. So this is important for, especially for many of you coming from land development. You need to have a basic understanding of hydrology in order to, properly design your stormwater infrastructure, and that's what we're going to be talking about for the next couple of class sessions. Okay, I wanted to revisit one question that a couple of students had about homework 1, and this has to do with the channel transition problems. So on problem, I believe 1.5, you have flow encountering a transition in the channel width, okay? And this also affects the depth of flow at that location. So in problem 1.5, you're asked to find the critical depth or design the width transition to cause critical flow to occur. And then you're also asked to determine the depth at the other side of the transition. And the question was, what happens to the flow after it encounters this transition? Does it go back up to the subcritical depth, or does it go down to the supercritical depth? For the purposes of your homework, either answer will be accepted. It is theoretically possible for the flow to either return to the subcritical depth or to the supercritical depth. But in practice, it will almost always go down to the supercritical depth. You can achieve the subcritical depth at the opposite side of the transition under carefully controlled laboratory conditions. But in practice, if it transitions through the critical depth at this transition, it'll almost always go down to supercritical. And so for that purpose, either answer is acceptable for the homework. Okay, great. All right, are there any other questions before I move on to the material for today? Any other questions? No? Okay, cool. So what I'm going to do now is I'm going to finally finish up our discussion on open channel flow. The last topic I'm going to talk about is discharge control structures. Okay, in particular, we're going to be revisiting two discharge control structures that you probably encountered in hydraulics. There are two main ones that we need to understand how to model, both for the purposes of design as well as for modeling of stormwater infrastructure. These occur in models such as HEC-GRAS, HEC-HMS, and SWIM. The first discharge control structure is an orifice, and the second discharge control structure is a weir. And there are two types of weirs that we'll need to consider. The first is a sharp-crested weir, and the second is a broad-crested weir. So in the interest of time, I'm not going to go through the full derivation for the equations for each one of these control structures. I will just briefly visit each one and give you the equations that you will need for the homework. This is largely a review from hydraulics. Okay. Okay, so first let's talk about orifices. So what is an orifice? Remember from hydraulics, these occur a lot in stormwater infrastructure, particularly at the outlets of impoundments such as detention basins. So let's say you have some sort of detention basin. Okay, you have water in the detention basin, and you can assume at this location, the water is essentially static. It's not moving, so its velocity in this area is 0. You have some opening, so this is the orifice. You have an opening, it may be at some distance above the bottom. And out of the orifice, you have essentially flow coming out at atmospheric pressure. So you have the discharge coming this way, this would be Q. The area, the cross-sectional area of the orifice is given by A. So we'll call this the cross-sectional area of the orifice. And the depth from the centroid of the orifice to the water surface at the upstream side is given by delta H. We'll call it delta H. Okay, so this is essentially the head difference between the upstream end and the downstream end, which is exposed to atmospheric pressure. Okay, so for an orifice, the equation that describes the discharge through the orifice is given by the discharge Q is equal to C times A times root 2G delta H. Okay, so you might remember this from hydraulics. Q is the discharge. This might be in cubic meters per second. C is the discharge coefficient. Okay. And it usually adheres to a value of about 0.6 or 0.67. So you usually assume discharge coefficient is about 0.6 for most purposes. A is the cross-sectional area of the orifice. G is the acceleration due to gravity, and delta H is the depth above the centroid of the orifice. So one nice thing you might notice about this equation is that it gives a one-to-one relationship between the depth and the discharge. And this is characteristic of all of the control structures that we'll be talking about, which is why they're often used for the purposes of flow measurement. Okay. Are there any questions on the orifice before I move on? Any questions? So this is largely a review of hydraulics. Okay, the next control structure we're interested in is the sharp-crested weir. Okay, so these are often placed in the channel intentionally for the purposes of flow measurement. As I just mentioned, all of these control structures have a one-to-one relationship between the depth or the head difference across the control structure and the flow. And in general, it's much easier to measure depth than it is to measure flow. So an easy way to measure the flow is to essentially just measure the depth at the control structure, the depth of the water at the control structure. Okay, so a sharp-crested weir essentially consists of a thin plate mounted perpendicular to the direction of flow. Okay, so I'll draw the plate in red here. Okay, and you have some depth of water coming in. It gradually transitions down and then overflows over the top of this plate. So this is Q. And what we're interested in here is the depth above the top of the plate. So we'll call this H. This is essentially the head above the top of the plate. This is measured at some distance upstream of the sharp-crested weir. So note that you'll have some head H located upstream of the weir. As it approaches the weir, it'll actually, that depth will decrease until it goes through the critical depth, and then it will discharge over the top of the weir at atmospheric pressure. Okay. So the equation, just note that if we look at this kind of as a view, a cross-sectional view, let's just say that's the channel, and we might have, the weir like this. Let's just say that the width of the weir is given by B. Okay, so this is the distance of the length of the weir. And the equation for our weir is given by Q, the discharge, is equal to CW, our weir discharge coefficient, times the length of the weir, times the head over the weir to the 3/2 power. Okay. And this is the weir discharge coefficient. Note that this is for a rectangular weir. You can also have triangular weirs that have a slightly different equation, which I will include in the type notes. This weir discharge coefficient also depends on what unit system you're using. So I won't give a value. For SI units, it's usually around 1.84, but it depends on what unit system you're using. Okay, and B here is the length over which the discharge is occurring. It's the length of the weir, and H is the head above the weir. Okay, so that is the sharp-crested weir. In practice, weirs that will naturally be encountered are of the broad-crested variety, though. So let me show you a broad-crested weir next. And essentially, a broad-crested weir is a device that's used to essentially create the critical depth over a portion of the channel. Okay, so much like the problem we examined last time in class, we can cause a change in the water surface elevation by adding a transition in the bottom elevation of the channel. And that's essentially what a broad-crested weir does. Okay, you have a channel and you have a structure that kind of rises above the bottom of the channel. And this structure causes the water surface to drop until it reaches the critical depth over the structure. Okay, so we obtain HC over the structure. Okay, and I'm just going to call this this length here H. So this is the head above the top of the weir. So this is essentially much like the channel transition problem we looked at before. This is a device for creating the critical depth within the channel. This is often also used, as I'll show in a second, to model flooding over obstructions such as bridges. Okay, so this model is often used, and you will see that when you look at HEC-RAS later on in the class. It uses weir flow to model flooding that is occurring over the bridge. Okay, so for the broad-crested weir, I will give you the equation. Let's just take another cross-sectional view. Let's just say this is the width of the channel, which is the same as the width of the weir, and this is given by our length B. The equations for the broad-crested weir can be obtained, simply by applying the conditions for the critical depth. Okay, so we have from our critical depth condition, Q squared times the top width is equal to acceleration due to gravity times A cubed. So this is from 2 lectures ago. If we look at just a rectangular channel, this becomes Q squared B is equal to G times B cubed times the critical depth cubed. Okay, so this is the flow at this section where the critical depth is obtained. And from this, we can simplify and obtain an expression that gives us a one-to-one relationship between the depth and the discharge. And that is Q is equal to B times the square root of G times the critical depth cubed. Okay, so this is the equation for the discharge over a broad-crested weir. Yes.
Why would you want to connect the critical depth?
So one purpose might be for the purposes of flow measurement, right? If there's a one-to-one relationship between the depth and the discharge, you can measure the discharge by measuring the depth, because in general, depth is much easier to measure than flow directly. Yeah. And as I mentioned, this is often also used to model things like flooding over roadways. And speaking of that, I'm going to, oh, yes.
So if the, like in the channel, if like the flow rate was like increased, did the weir still, like in the transition point, would it still be the critical depth or would it be greater? If the flow rate that was designed for is like bigger than what it's designed for.
So this is, yeah, this would be for the steady state case, because ultimately it comes from the energy equation and the equation for the critical depth. I believe that, yeah, I believe that if you change the flow conditions beyond what the critical depth could be obtained over it, you may not have the critical depth over that section. That's an interesting question. There is a problem on the homework, though, where you have a situation that's similar to this, but in kind of a disguised form. Essentially, if you have a steep enough channel at the downstream end, you will obtain critical depth over some point in that transition. It may not be the exact same point, but you will still end up with critical depth because on the other side, you have to be super critical. So that's a good question. I'll think about it some more and think about under what conditions this no longer applies. But it's still a useful conceptual tool when you're thinking about flow that is essentially going from subcritical to supercritical on the other side. Yeah. Okay. Cool. So with that, I'm going to give you an example to work on. I'll give you about 5 or so minutes to work on this. Okay, so let's consider the case of flooding over a roadway. let's consider the case of flooding over a roadway. So let's say we have some roadway, we're looking at it from the stream's perspective. Okay, so here's the roadway. We're looking at it from the stream's point of view. And we have a culvert located inside of this bridge deck. Okay, so the flow is going essentially through the screen. We're looking at the direction of flow right now. And this is a culvert that is mounted in this bridge deck. The diameter of the culvert is going to be equal to 2 meters. Okay, there is a 0.5 meter gap between the top of the culvert and the start of the roadway here. So this is 0.5 meters. And we have flooding occurring on the roadway. So there's water on the roadway and water all through this section here. So the roadway is submerged to a depth of 0.3 meters. Okay. The length over which it is submerged is B, which is equal to 5 meters. Okay, so what I want you to do is, assuming the culvert behaves like an orifice, and the top of the roadway behaves as a broad-crested weir. I want you to compute the discharge, compute the combined discharge through both the culvert and over the roadway. So I'll write compute the combined discharge through the culvert and over the roadway. And note, you can assume this 0.3 here, the 0.3 meters is equal to the critical depth over the roadway. So this is actually something you are going to encounter later on in class during the project. I want to give you a quick conceptual overview of how you might formulate and think about this problem. Okay, so is there a question? This is a broad-crested weir, so you won't need a weir coefficient, but for the culvert, for the orifice, assume C is equal to 0.6. Yes. Okay, so I'll give you 5 or so minutes to work on that. All right. Hey, everybody. In the interest of time, I have to move on. So does anyone want to volunteer and answer? Yes. It's a bit too big. Anyone else want to volunteer and answer? 13.7, exactly. So how did we get that answer? I'm going to go through, I'll very quickly go through, but essentially we have 2 equations here. We have the orifice equation for the culvert, and we have the weir equation for the flow occurring over the top of the roadway. Sorry, the broad-crested weir. Okay, so the tricky part here, I think, is figuring out what this delta H needs to be, right? So the delta H is the depth from the centroid of the orifice to the top of the water surface above the orifice, right? So that includes half of the orifice, so that's 1 meter, plus 0.5, that's the distance to the beginning of the bridge deck, plus the 0.3, which is the depth of the water above the bridge deck. Okay, so once you add those together, you should get an answer of about 11.2 cubic meters per second through the orifice. And the flow over the weir portion, the flow over the broad-crested weir, we just apply the broad-crested weir equation with a depth of 0.3 feet above the top of the weir. Okay, are there any questions on this before I move on? Yes?
So you're driving the bridge, you like bicycle or you like cutting half long ways, like,
Yeah, so a car would look like this.
yeah, he's driving that.
The car is driving this way.
You like step up on either side then.
So that might be like the beginning of just the concrete portion, and then there's like a railing or something this way. I want to introduce you to this view because you're going to see this in HECRAS a lot when you look later on in the course. It's going to look something like this. There will be kind of these abutments over on the side a lot of the time, and then the roadway itself will look something like this. So these might be just concrete abutments. The car is behind them, so the car is not going to drive into the concrete. The car is behind these. And then the roadway has some depth to it, yes. Did you have a question in the front? No? Did you have a question? Yeah.
Kind of answered. I was like, oh, the two things are kind of like a wall. Like,
Yeah, yeah. So there would be like maybe concrete abutments kind of on those ends. This view you're going to see a lot later on in the class when we do HECRAS, so I want to introduce to it now. Okay. Great. All right, are there any questions on this example before I move on? I know it's a confusing visual. I just want to get you used to this view. I'm going to see it in HECRAS, as I mentioned. All right. So with that, let's move on to something completely different. For the next 3 or 4 lectures, we are going to be talking about hydrology. Hydrology for stormwater design. Has anyone taken or is planning to take the hydrology class offered by Professor Pasalacqua?
Oh, wait, it was a different, I don't think it's that. It was last semester and it was a different. It
So-
wasn't a professor. it was-
Jordan Furnace, maybe?
Yes.
Yeah, okay. Okay, so we're going to be covering some of the material they talk about in that class. But in particular, we're going to be focusing on the aspects of hydrology that are needed for stormwater design. So we're not as concerned with the physical processes necessarily, or the reasons why water behaves in a certain way within the hydrologic cycle. Here, we're mostly interested in determining how much water ends up in our stormwater system for the purposes of designing that infrastructure to accommodate those flows, okay? So we're interested in 3 primary questions when we're talking about hydrology for stormwater design. The first is how much rainfall occurs. Second, how much rainfall ends up as runoff. In other words, how much of the rainfall ends up as overland flow that travels across the land surface. And third, how much runoff ends up in the stormwater system. So how much runoff ends up as channelized flow. These are the 3 primary questions we're going to be concerned with that we'll be addressing in detail in the next couple of lectures. So how much runoff ends up as channelized flow. And these are all questions. Okay. So over the next, over this next 30 to 45 minutes, I'm going to take a more conceptual look at things. I'm not really going to go through many equations. Really, I want to give you a conceptual overview of the urban hydrologic cycle as it applies to stormwater design in particular. So we're just going to be discussing general concepts about how water moves through urban watersheds. And then towards the end of the class, we'll be talking a bit about how we estimate rainfall for the purposes of design. Okay. Are there any questions before I move on? Great. Okay, so let's take a look at the urban water cycle, the cycle of water within urban watersheds. I want to take kind of a broad conceptual view and kind of just discuss all of the different things that can happen to water, how water moves throughout this cycle, and just kind of give a broad conceptual overview of all the different processes we're interested in. Okay, so let me draw a land surface here. Okay, so I'm going to be spending the next 10 or so minutes just drawing a big picture for you, but I think it will be helpful. Okay, so I'm going to draw these little bumps. You'll see what those are in a second. Okay. Sorry? Oh, well, I'm going to give you a tree right here. Yep. It's going to be like a mini Bob Ross lesson here. Going to have a happy tree right here. Okay, so we got a happy tree. We got some happy roots coming out. Okay, so you have a tree. Okay, land surface is going to continue to run, and then there's going to be a big dip here. Okay, okay, so that's our land surface. Some grass or something here. All right, and we have a line here. This is going to indicate the water level. Actually, let me draw it a little bit lower. Okay. So we have water here. Okay. So this indicates the water level both within this channel here, as well as underneath the surface of the earth. So this part here, this indicates channelized flow. This is the kind of flow we've been dealing with for the past 4 or 5 lectures. So you can think of this as a river or a stream. Okay, and this line here, as it extends through the channel and through the surface of the earth, this indicates the water table. Okay, so you can think of this as the water table, and we'll divide the soil into 2 sections. Above the water table, we have the unsaturated zone, sometimes called the vadose zone. And underneath the water table, we have the saturated zone. Okay, so what happens to water as it lands on our watershed? Let's just draw the precipitation as it's coming in. Okay, so we have some precipitation. Now, precipitation can be, it can be snow, can be sleet, can be hail, any of those things. But in this class, we're primarily just going to be concerned with rainfall. Okay, we're not really going to worry about other kinds of precipitation. So let's label this. This is precipitation. And let's think about all the things that can happen to this precipitation as it lands on our watershed. Okay, so one thing that can happen is that the precipitation can land directly on the channel. And this is something that occurs when the precipitation lands on the channel. It causes the water surface to rise very rapidly. So you'll see a very steep increase at the beginning of the hydrograph, often due to water landing on the channel or due to water landing in reservoirs in the river network. So it can land in the channel itself. It can land in these little depressions in the surface. Okay, so the water can end up as, this is called depression storage. So water can end up just kind of trapped in little depressions on the water surface, on the land surface. The water can land on vegetation. Okay, so it might get trapped kind of in the leaves or grass. And this is often called initial abstractions. So there's some portion of the water that gets caught just on various places where it can't enter the larger drainage network. That's often called initial abstractions, and depression storage is also part of those initial abstractions. And for the rest of the water, a couple of different things happen. So this is this is kind of the large majority of what's going to happen to the water, is one of two things can really happen here. The first is that the water infiltrates. Okay, so we have a portion of the water that infiltrates. This is infiltration, infiltrates into the soil. That was really messy. I'm going to rewrite that here. So this is the portion of water that infiltrates into the soil. And the other big fraction is the runoff or overland flow. So water will land on the land surface, where it eventually flows down the land surface as overland flow into channels downstream. So this is, I'll just call this overland flow. So those are the two main components, and those are the two main components we're really going to be interested in for this portion of the class, is determining the fraction of water that infiltrates and the fraction of water that ends up as overland flow and channelized flow later on. Okay. I just want to discuss a little bit more about infiltration. So when the water infiltrates into the soil, there's a couple of different things that can happen. The first is recharge. Okay, the water can essentially continue moving down into the water table, where it recharges the water table and causes the water table to rise. It can also be absorbed up into plant roots. So, okay, I'll call this plant uptake. So a portion of the water gets sucked up by the plants, either the trees or the grass. Once it gets sucked up into the plants, it can be discharged into the atmosphere through evapotranspiration. Okay, so this is basically the process by which trees exhale the water stored inside them into the atmosphere. And you may also have a portion that just evaporates from the depression storage or from the land surface itself. So you might just have regular evaporation without the transpiration component. I'm going to erase this line here so I just have more room to write. Okay, and finally, there's one more way that water can move within this system, and that is through the unsaturated zone itself. So this is often called interflow. This is, I'm going to write this over here. This is interflow. And this is the movement of water through the unsaturated zone or through the vadose zone. And this can occur either just by water moving through the soil matrix itself or through structures embedded in the soil matrix, often what are called macropores. So macropores essentially consist of things like desiccated plant roots, holes left by burrowing animals. And even though they make up a relatively small fraction of the soil volume itself, flow travels very rapidly through them, meaning that it often comprises a large component of the water that ends up in the stream downstream. And really, this portion of the flow here, even though it's so important, is very poorly understood in hydrology, and it's an active area of research. Okay, so those are essentially all the ways that water can move throughout our urban water cycle. In this class, we're primarily concerned with just a couple of these components of the hydrologic cycle. The first is channelized flow, which we've spent the last couple of lectures talking about. We're interested in the precipitation, how to estimate it. We're interested in the infiltration. We want to know how much water infiltrates. And we also want to know how much water ends up as runoff or overland flow. So these are the four main components of the hydrologic cycle we're really going to be interested in. For the other components, I recommend taking hydrology with Dr. Pasalakwa or whoever is teaching it. It's a really fascinating subject where it gives you more expertise on kind of the physical processes and the science behind all of these different components of the water cycle. Okay. We're going to be discussing each of these four areas in turn. So let me just give you kind of a preview here. We're going to be discussing each of these components of the water cycle and how they relate to stormwater design. So channelized flow, we've already talked about. Okay, this can be modeled by, for instance, the St. Venant equations. We can analyze it using the energy equation. We can analyze it using Manning's equation. So this is essentially the component of the water cycle that takes place in the channels itself, and this we've already looked at. Let me just write Manning's equation. Okay. But we're interested in these other three components as well, and that's what we're going to be talking about over the next couple of classes. Precipitation. Okay. We're mainly going to be looking at precipitation through the lens of design storms. Okay, so we want to know how much precipitation occurs or is expected to occur at a given location. And through that, we can analyze essentially the amount of precipitation that will occur through what are called design storms, which I'll be talking about today. We're interested in infiltration. So we're going to be discussing a couple of infiltration models that are used in the hydrologic software you're going to be looking at later on. So we're going to in particular be looking at the green amped model of infiltration. And we're going to be looking at the Soil Conservation Service or SCS method. And finally, we're going to be looking at the concept of overland flow, right? So in addition to modeling the infiltration, we also have to model how water travels over the land surface before it gets into the channel network. And we're going to primarily be looking at that through the lens of what's called unit hydrograph theory. Okay. And these methods here correspond to the methods that are going to be used in the hydrologic and hydraulic models we'll be looking at later in class. So I think it's really important to understand these methods before you apply them using the models later in class. So I want to give you some context for all of these, okay? Great. Are there any questions on where we're going before I move on? All right. Quickly, before I begin our discussion of rainfall, I want to talk a bit about watersheds. I want to talk a bit about watersheds. So who here is familiar with the term watershed? Okay, most of you. What is a watershed in your own words? What is a watershed? First, oh, yes.
It's like a ditch that has some plants in it. Water collects.
That could be a watershed. But more generally, though, what is the concept of a watershed? Kind of more generally. Yes. Exactly, right. So a watershed is essentially a land surface where you can think of all of the water that lands on that land surface as draining to a common outlet, usually a channel. Okay, so let's draw a picture of a watershed. Okay, so a watershed will often look like this. By the way, what watershed are we in right now? Do you know your watershed? We're in the Waller Creek watershed. Very good. And Waller Creek is somewhere very nearby this building. I think it's like right over there. Okay, so watersheds are often defined by the channels that run through them, or the largest channels that run through them. So let's just draw a picture of a watershed here. A watershed consists of the land surface that drains to a common outlet. Okay, and you'll often see channels running through this watershed. Okay, so we have channels, look something like this, that kind of have a tree structure. And each of these channels will have subchannels coming off of it. And kind of the key feature of a watershed is that any rainfall that lands in this watershed will all drain to this common outlet here. So when we're doing modeling and we want to know what the stream flow or the depth of the water is at this outlet point, we only have to consider what's in this watershed here. We don't have to worry about anything outside of it because all of the water will drain to this common point. Okay. Another key feature of a watershed is that they have kind of this nested structure to them. So if I take this watershed and I define a new outlet point here, I can delineate the new watershed that drains to that point, okay, which will be something like this. So we can take this watershed now, and now this is our new watershed. Okay, and we can draw it like this, and we have the same stream network in there. I'll try to draw it the same as it was previously. Okay, so we can take our watershed and we can divide it up into infinitely many sub-watersheds. So every point on this drainage network has its own watershed inside of it. So I could, in fact, take another point inside this watershed, define an outlet here, and I can create a new watershed from just this part. We're going to be doing this in homework 3. We're going to actually be delineating watersheds using ArcGIS based on digital elevation model data, which is going to be really cool. But I want to give you kind of a heads up on this idea that watersheds are recursively structured. Okay? Have kind of these like recursive tree structures, and you can divide a watershed into infinitely many sub-watersheds. Okay, so we can think about watersheds as kind of a control volume for when we do our hydrologic modeling, in that any water that lands on it will all drain to a common outlet. Okay, are there any questions on watersheds? Yes. Sorry? Yes, so the Waller Creek is a sub-watershed of the lower Colorado River. Yes, because it drains to the lower Colorado River. So that also includes, for instance, Shoal Creek. All of the other watersheds in Austin will drain to lower Colorado. Yeah, very good. Okay, any other questions on watersheds? Yeah, you'll get familiar with watersheds on homework 3. Okay, so I want to shift gears a little bit. And I'm going to talk about rainfall. I'm running a little bit behind where I wanted to, but that is okay. Yeah, let's talk about rainfall. And for stormwater design in particular, we want to understand how to estimate the amount of rainfall that occurs for a given location, so that we can design stormwater infrastructure to accommodate that expected rainfall. Okay, so let me just kind of quiz you about how rainfall data is collected. How do we measure rainfall? How do we estimate how much rainfall is occurring at a given location? How can we directly measure rainfall? Yes, rain gauge. Does anyone know the particular name for the rain gauge that's commonly used? So one way to measure rainfall is through a rain gauge. And these are often called tipping bucket rain gauges. I have used these in the past. Okay, so it essentially consists of a bucket, like a cylinder. At the top of the cylinder, you have a funnel. The rainfall falls down into this funnel, it flows down here. And then on the inside of the bucket, you have a kind of this little cup mechanism. So these two cups attached together. And the rainfall falls into those cups and causes it to tip one way. And then once that cup fills up, it tips the other way, then it tips the other way. And from the number of, essentially the number of times the cup switches, you can determine how much rainfall occurred in a given location. Okay, so that's one way we can measure rainfall. What's another way that we can measure rainfall? What's another common way that we measure rainfall in practice? There's another major one. Yes. Basically, yeah. Yeah. So what's does anyone know what the name for this technology is called? Sorry? So the one I'm thinking of is weather radar. So you've probably seen this on TV. You'll see images of kind of these clouds moving, and they have this color scheme with the different intensities of the rainfall. You know, red is more intense, and you'll see these clouds moving across a map. Does anyone know how this technology works? Does anyone know how we get these maps of rainfall? So this technology, oh, yes. Close, but instead of light, we're talking about radio waves. So this technology was originally developed in World War II, and initially they were using it to detect enemy planes. So they would send out radar waves. The radar waves would bounce off the planes. And you've probably seen the movies where they have the little tracker going around and you can see the location of the planes. But what they found was that when those radio waves encountered moisture in the atmosphere, that caused the radio waves to reflect back. And so they would see these shadows on the radar scope that they first thought were enemy planes, but it turned out it was actually due to storms. And so they figured out that they could create these empirical relationships relating to reflectivity to the rainfall rate. And that's where we get weather radar from. So weather radar gives us a nice spatial picture of how the rainfall is moving, over our area of interest, but it has some errors associated with it that make it often less reliable for a given point than a tipping bucket gauge. So both of these rainfall measurement techniques are needed to get a fuller picture of how much rainfall is occurring. Okay. For the purposes of engineering, though, we're often interested not necessarily in the amount of rainfall that is occurring at a given location and time, but rather the expected rainfall that might occur in a given location so that we can design infrastructure to accommodate that. And does anyone know what the primary technique is used, what the primary technique is called for assessing those expected rainfall values? Okay. It's a couple different answers. What I'm going to call them is, yes.
Wasn't one of them like Pearson 3?
It sounds like a statistical.
Or is that just...
That might be a name of a particular product. The more general name that I'm looking for is design storms. Okay, so a little simpler. And in particular, what are called IDF relationships. Okay, so these are intensity, duration, frequency relationships. Okay, so rather than understanding the exact amount of rainfall that's occurring at a given location at a given time, it's often more useful in design to understand kind of the statistical properties of rainfall in a given area so that we can design infrastructure to accommodate it. Okay, so IDF curves are used very commonly to estimate the stormwater loads on our hydraulic infrastructure. And we often do that through these IDF relationships, which consist of 3 parts, essentially. The first is the intensity. Okay, and this refers to the rainfall intensity. in units of depth per unit time. Okay, so this is in units of depth over time. So for instance, inches per hour of rainfall. We have the duration. So this refers to the expected duration of the storm event. So I'll just say rainfall duration. And this is in units of time. And finally, we have the frequency. And this refers to the expected return period of a storm of a given magnitude. Okay, so this is also in units of time. Okay, so who's heard of a 10-year storm or a 100-year storm? Has anyone heard those terms? So that refers to the frequency or return interval of the storm. So you can essentially expect a storm of that 100-year storm. You can expect of a storm of that magnitude to occur every 100 years based on existing historical data. Okay, and in many cases, those expected return intervals in the magnitudes of the storms they're associated with are changing due to changing climate. So in fact, the Austin Drainage Criteria Manual was recently updated to update a lot of the magnitudes for our return intervals. Okay, so IDF relationships, these are compiled. Oh, yes.
For like that concept, is it like the storm is likely to only happen like of that magnitude, like 1%, or is it actually kind of it will only happen in a year?
It's 1% chance of it occurring in any given year.
Okay.
Yeah, based on historical data from the past, however many years they looked at to determine these curves, which is often less than, you actually need to characterize that distribution. But yes, for a 100-year storm, that means there's a 1% chance of it occurring every year. Okay. And note for the magnitude of the storm, you need to account for both the intensity of the storm as well as the duration of the storm. Okay, so you may have a storm with very high intensity. So for instance, 10 inches per hour, but it may only occur for 30 minutes. Oh, did you have a question?
Yeah. When you what surface area is
So yeah, so like over the entire watershed, it would be 10 inches of rainfall at every location in this watershed, basically. So there is you have a volume of rainfall that falls, and then you just divide it by the surface area. So you can think of rainfall as being measured in inches, essentially. So inches of rainfall really refers to the volume divided by the area over which it falls. Yes. Mm-hmm. Okay, cool. So these design storms are compiled for different locations. Every city, county, every region has their own IDF relationships corresponding to their particular climate. They're compiled either in graphical form or in functional form. So I'll show you both of those. So under files here, this is a plot of the IDF relationships. I believe this is for Phoenix, Arizona. And you can see on the y-axis, we have the rainfall intensity in inches per hour. On the x-axis, we have the duration of the storm. And each of these curves represents a different return interval. Okay, so this top curve here, this is the most intense, and this is the 100-year storm. So let's look at just a couple of different points on this curve. Okay, for a duration of 2 hours, our intensity of the storm is roughly 1.5 inches per hour. So let me write this down. So for a 2-hour, 100-year storm, the intensity, okay, so let me just say for graphical IDF curve, the intensity was approximately 1.5 inches per hour. Okay, let's take a look at another point on this curve. So let's look at 15 minutes. Okay, for the 100-year storm, the intensity for a 100-year 15-minute storm is roughly 6 inches per hour. Okay, so for a 15-minute 100-year storm, this is roughly 6 inches per hour. So what's the total volume of rainfall that fell for each of these storm events? What about for the 2-hour storm? All right, 3 inches, right? And what about for the 15-minute storm? 1.5 inches. So note they will have different total volumes of rainfall that fall. What the IDF curve gives you is the intensity associated with a given duration and recurrence interval of a storm. Okay, another way that we can express IDF relationships is in functional form. So for the Austin drainage criteria manual, we are going to be using the following functional relationship to obtain the intensity associated with a given duration and recurrence interval. We have that the rainfall intensity, which I'll call W, is given by the following empirical equation: A divided by the rainfall duration plus B to the C power. Okay, so W, this is the rainfall intensity, and this is in inches per hour. TD, this is the rainfall duration. And this is actually in minutes for this equation. So it's not dimensionally consistent. This is an empirical equation. The units aren't necessarily consistent. And A, B, and C are empirical parameters that depend on the recurrence interval or the expected return interval of the storm. So I'll just say recurrence interval. So these will change depending on whether you have a 10 or 100-year storm or a 1,000-year storm maybe. So let's take a look at these and let's do an example. Okay, what I want to do is I want to go through for the last 5 minutes how we can compute the expected intensity using the Austin drainage criteria manual. Okay, so I want to use our equation, use IDF function. Okay, and let's say we have for a 2-year storm event with a duration of 3 hours. And I want to compute the intensity. What is the intensity of a 3-hour storm for a 2-year storm event? Okay, so we can do that by essentially looking up the A, B, and C parameters from the Austin drainage criteria manual, which I'll show you how to do in a second. So let's go ahead and write out that equation again. We have W is equal to A divided by TD plus B to the C power. And essentially what we need to do here is we need to find this A, B, and C parameters by looking at the Austin drainage criteria manual. So I'm going to go ahead and do that. You'll also need to do this for homework too. So I'm kind of giving you a tutorial for how to do that right now. Okay. Okay. So if we go to Canvas, I have uploaded a link to the Austin Drainage Criteria Manual under Pages. And we'll be using this a lot throughout the semester, so I want to help you get familiar with it. What we'll need to do is we need to go to section 2. We're going to go to Design Rainfall. And the Austin Drainage Criteria Manual compiles our IDF relationships for different regions throughout the city. So let's just say we're in zone 1. Okay. The Austin Drainage Criteria Manual will give you these depth, duration, frequency values. And here is a table for zone 1. Sorry, this is actually giving you the depth associated with each of these storm events. We want the parameters A, B, and C. So we can find those. If we scroll down a little bit, here we go, intensity, duration, frequency. Here's that equation I showed you. And essentially we just go to this table and look up our A, B, and C values that we need for a given duration and return interval. So what is the correct value for A, B, and C from this table? Yeah, so it's this first row here. So our A will be 45.24. Our B will be 9.339. And our C will be 0.7399. So in the last minute or so of the class, I want someone to go back to that equation and compute what the expected intensity is, okay? And challenge you to be the first to answer. Okay. And whoever can figure out the answer first, just raise your hand and yes.
0.9345.
0.9345. Is that in inches? So remember that this TD value, this is in minutes.
Yeah, I put 180.
You put 180? Okay, that's probably right then. Yep, okay. Okay. All right, I'll see you all on Tuesday. Don't forget to come to office hours if you have questions about the homework. All right. I'm sorry?